Hi everybody, I hope everything is going well in light of recent events. So this will be the second class video since the beginning of the apocalypse. And we will be covering section 14.6, which is using the estimated regression equation for estimation and prediction. So that's straight out of the book. I'll be following pretty closely with the book. I'll also share these notes that I'm writing with you. I'm going to try to go through these relatively quickly so the video isn't too long, but you'll have, of course, the opportunity to rewatch the video and just look over the notes because I'll send those out with the video and an announcement. So first, let's start with some review. So recall that the population equation for regression, for simple linear regression, meaning we have one independent variable, looks something like yi equals beta naught, the population intercept, plus beta 1, the population slope, times the independent variable plus a set of population error terms. An example of that might be, so e.g., for example, home price equals beta naught plus beta 1 square feet plus that population error term. So that would be following a research question such as, does square feet affect home price, which would be a two-sided research question, two-sided hypothesis test, or something like, do square feet increase home price, which would be a one-tailed hypothesis test about the slope, the population slope right there, because that's really what we usually care about in regression, is the relationship between the two variables, which is defined by the slope term. Now, a sample equation is very similar. So the sample equation, now we just kind of change the parameters. This is kind of like going from mu, the population mean, to x bar, the sample mean, but now we're using equations. So we'll have yi equals b naught, a sample intercept, plus b1 xi plus ei, a set of sample errors. That's what that ei is, sometimes called residuals. And notice that this is just a placeholder. This is a general sample equation, but if we were doing this for our home price example, our sample equation would actually have numbers because we'd get those estimates. So we got to go get a bunch of data on home prices and square feet. And we find the following sample equation. So square feet right there plus EI. And so home price, we could label that by I2. So for home I, the home price is home price I. We'll have this measured in thousands of dollars. So maybe an empty plot of land is $75,000. But then as we start building houses on that land, the value of the land or the home price increases because now we have a house. And this slope is the rate it increases. So let's do a slope interpretation just for practice. If number of square feet increases by 1, then home price increases by $0.15 thousand though. So that would be about $150 per square foot. So that's an example of a sample linear equation. Now, a question we've asked in the past, we're not going to cover in this video, but we'd want to know how to answer the following question. Is B1, our slope estimate, equals 0.15 statistically significant? So know how to answer that question. So you'd have to have some other information. Is this a one-sided test, a two-sided test? What is the standard error of that estimate? Because that's a random variable. And then we'd have to turn that into a p-value, for example. Excel will do all that for you, but recall that you'll have to know how to do that. That is not the topic of today's lecture, so we'll move beyond that. So a new goal in the past, we've been focused on that slope. Now we're going to be focused on a new goal that oftentimes regression is useful for. So our new goal is predict values of y given values of x. So predict values of the dependent variable given values of the independent variable. So I've mentioned in class, this was basically my job as an energy analyst in the past. I was trying to predict values of natural gas storage given a lot of different independent variables. That can often be the most useful thing to be able to do in a business environment, is predicting values of y given different values of x. And that's what we're going to be working on today. So we can keep going with our example. Would be to predict home prices given square feet. Okay? So that's going to be the topic of this session. So we're going to be focused on estimation and prediction. So we're estimating or predicting values of y given values of x. Now, a little bit of this will be review. For example, as you know from chapters 7 and chapter 8 at the beginning of the semester, there's two types of what prediction. So there's point estimates and interval estimates. So a point estimate is, this is my single guess of y. That's what a point estimate is. A single number that is a guess of a y value given some values of x. Now, we know that we're not going to get the perfect guess every time. Just like we don't know we're not going to get the perfect guess of the population mean given a sample mean each time. So oftentimes we like to reflect that uncertainty using an interval estimate. And we'll be able to do both of those things with regression, just like we did when we were looking at trying to predict population means or differences in means. Both of these types of estimates always existed in those cases. So now we're just expanding that to regression. So y hat, the predicted value of y, will always be the point estimate. So we'll just plug in the values of x into our regression equation, and whatever our regression equation spits out, that will be our point estimate for y. So we will choose some x star value, the value of x that we are interested in guessing the value of y for. We always have to pick that. We have to pick the x we're going to stick into the equation to guess the value of the dependent variable. So then once we choose x star, then y hat, maybe we'll call that y hat star because it's the y hat that is associated with x star, will equal b naught plus b1 x star. So we're just sticking that special value of x that we picked into our equation, and that's going to be our point estimate. Now notice we don't have the air terms in there. That's because the air terms on average are equal to 0. So they cancel out when we're looking for our average guess. So that we're taking the value of y off of the line that we predicted that is associated with x. Now for example, suppose x star equals 2,000 square feet. And we're going to guess the value of homes that are 2,000 square feet using our sample regression equation. So we have home price star, because that's going to be the home price associated with this x value we picked, equals 75 plus 0.15 times 2,000. And if we crank that out, we get 375. So our point estimate for houses of size 2,000 square feet is that those houses will be worth $375,000. Because remember, these are measured in thousands of dollars. So the point estimate, you just plug in the x value that you want the y value associated with. So there is a point estimate for houses of 2,000 square feet. Our point estimate of the home price given our sample equation is $375,000. Now that's just a point estimate. We don't know how spread out our values are around the regression line. Maybe that's a really bad estimate because we have a really noisy data set. Or maybe that's a really good estimate because we have a really, really strong, tight relationship between square feet and home values. So the point estimate is pretty easy. Just plug in the value of x that you are interested in getting the value of y for. Your equation will spit out the point estimate. Interval estimates, on the other hand, get a little bit more complicated. And so let's recall that the margin of error, we have this general formula that we've gone over many times in class, is equal to my standard error times how many SE I need to go. So this will be now a standard error for a y hat value. So notice that this margin of error formula has not changed. What has changed is, well, what are we getting the standard error for? Now we're getting it for a y hat, a predicted number from a regression line. This will be a t critical value, basically, that tells you how many standard errors you have to go. So those are always the two components. Nothing has changed about that. All that's changed is our new estimate is now a y hat, and that's going to have a different standard error formula than before. So that's the important thing to remember here. So there's also a distinction between two things that's important. So we have confidence intervals. This is going to be guessing average value of y given x. So for example, maybe I'm going to look at 1,000 homes that are all 2,000 square feet. And I want to know, the average value of those 1,000 homes. Then I will use a confidence interval. because I'm guessing the average value of y given x for a bunch of homes. Notice that to talk about an average in a meaningful way, we have to be talking about a bunch of observations. So if I'm asking the question, I'm going to build 1,000 homes that are all 2,000 square feet. I want to guess the average home price for all those homes. Then I am in the confidence interval world. On the other hand, the other thing we're going to look at today is prediction intervals. Prediction intervals are intervals if I'm guessing one value of a home price given one value of x. So for example, I'm going to build one house with 2,000 square feet. What is my best guess at the home price for that one house? Prediction intervals will be wider than confidence intervals because as we know, when we're just looking at one value, we're going to get more spread out guesses, more errors, more likelihood of outliers. So the main difference between confidence and prediction, if I'm looking at a big group guessing the average, I'm going to use confidence. If I'm looking at one individual value, I'm going to use prediction intervals. So guessing one value of y given x. The book has a good example of this too. I encourage you to look through the same information in the book, compare it to what I'm providing, and that should give you a strong understanding of the difference between these two. They use a company that's building pizza shops in their example. So now one thing to note about regression that we haven't talked about yet is that, so here I'm going to have an x and y axis, x, y. I'll go get some data. Let's assume we're still dealing with our home price square feet example. Now I'm going to get a regression line from Excel. It's going to give me the equation of the line, whether I do a scatter plot or whether I do the data analysis tool pack. One important characteristic of these regression lines when we use least squares is that there's a special point that's on every single regression line. That point is x bar, y bar. So in other words, this blue regression line will always go through the point x bar, y bar. Notice that that point is not necessarily in the data. You could have a sample average where the sample average for x is not actually the same as any point in the data. In fact, that will usually happen. Same with y bar. But that point, x bar, y bar, is always on your graph, and that's going to help us think about confidence intervals. So let's suppose for our example, our home price example, that x bar equals 2,000 equals average square feet. Sample average square feet in our data. Let's assume that y bar, in fact, we already know what y bar has to be because remember the point x bar and y bar is always on the graph. Well, we already plugged in the value 2,000 above into our equation, and what did we get? We got $375,000. And it turns out because this point is always on the graph, we know that that is the average home price. Okay, so this point is always on the graph. And not only that, but our confidence interval will be the tightest around y bar because we have the most information about our data near the mean. Notice that for really high values of x, we have less information. For really low values of x, we have less information. But for the average, we have the highest amount of information. When we have more information, we have less uncertainty, and we're going to have tighter confidence intervals. So it turns out that the standard error for y bar, when we're looking at the mean value, is s over the square root of n, which you already know because that's what we've been using the whole time for confidence intervals for sample averages. That is always our standard error for the sample average. We're going to write this as s 1 over n, because this is going to help us think about some other things in a little bit, but those are exactly the same equation. And in the context of regression, s, the standard deviation, which is actually now called the standard error of regression, is going to be calculated a little bit differently, and you'll have to remember how to do that. So that's going to be s equals sum of squared errors, which we've gone over how to calculate that before. You don't need to use the crazy equation to calculate that because Excel will spit this out for you, divided by n minus 2, and it's going to be the square root of that. So that's what s is in these equations above. So you'll just need that formula to calculate it. I'll show that in the next video when I do this stuff in Excel, how to actually do that. So that's going to give you your standard error, and now the question is how many standard errors to go? Well, we're going to be using t distributions. T dot inverse gives us t critical values. We'll have to feed that an alpha and a degrees of freedom. So alpha, depending on what your confidence interval is. So for example, if you were doing a 95% confidence interval, you would put 0.025 in there. Or 0.975 would probably be easier because you want 2.5% in each tail. And the other thing that's going to ask for is degrees of freedom. And in regression, degrees of freedom is n minus 2, which is another thing you'll have to remember for calculating these guys. But notice, so in this case, my standard error, how many standard errors I need to go are pretty straightforward, stuff that we've looked at in the past. So now just to implement that, let's kind of go through a couple of questions. So question: what is the true average home price for 2,000 square foot homes? Notice that we're talking about what is the average, not an individual value, but the average. So we're in the world of confidence intervals. The answer for the point estimate is 375, which we already saw because we already just plugged in 2,000 to our equation. We've also mentioned that this 2,000 is x bar. So now let's produce an interval estimate. That's our point estimate. Our interval estimate will be 375 minus t alpha over 2. So that might be the critical value with 2.5% on the outside, for example, if we're doing 95%. That's how many standard errors I need to go. We need to multiply that by my particular standard error, which is going to be s times square root 1 over n, comma, 375 plus ... That's going to be plus the same thing. This right here is the margin of error. How many standard errors do I need to go? What is my particular standard error? So in that case, we're right at the mean. Because remember, x bar is 2,000, y bar is 375. That's going to be my simplest case for confidence intervals. Now let's suppose we asked about a different value of x that was not x bar. So question, what is the true average home price for 3,000 square foot homes? Now A, the point estimate will be home price hat star for this special value of x, 3,000, equals 75 plus 0.15 times 3,000. That's going to equal 525,000. That's my point estimate. Just like before, we just plugged it into the estimated equation. Okay? Now our interval estimate's going to get a little trickier here because now we're going to have the standard error for y star. Notice I'm not putting y bar there now. I'll just put y hat star because before we were looking at the sample average, which we knew was on the graph. Now we're looking at this 3,000 value for x, which is not the same as the sample average. So now we've moved away from the sample average. We have less certainty, more uncertainty. Our standard error will get bigger to reflect that. So here we'll have S, where that's SSE divided by n minus 2 as mentioned above. Square root 1 over n, that's the same as before. So we still have this standard error around the mean, but now we're moving away from the mean, so we kind of have to add that extra uncertainty. And so how we reflect that is x star, which in this case would be 3,000. That's the x we're interested in looking at, that 3,000 right there. That's what we would plug in for x star if we were doing this. But we could do that for any x star. So in this particular case, it would be 3,000, but I'm writing the general formula, minus x bar, so the distance between the particular x star you're interested in and x bar. Notice that before we were looking at 2,000, so our x star was 2,000 and our x bar was 2,000, so this was 0. So we actually used the same formula, but now it doesn't evaluate to 0. In this case, it would be 3,000 minus 2,000, which would be 1,000. And then we're going to go ahead and divide that by sum xi minus x bar squared. This bottom is a measurement of the total variation in x. Notice if the total variation in x right here, so this is the total variation in x. If I have a lot of variation in x, then I have a lot of information about x values and y values that are far away from x bar. And then I'm going to have less of a penalty for moving away from x bar because this number is going to get bigger. And that's going to help me because a big variation in x means I have a lot of information about different values of x. On the other hand, if I don't have much variation in x and I look at a really far away value from the sample, I'm not going to have a lot of information. I'm going to have a lot of uncertainty, and this is going to get bigger. So it's worth thinking. This is an intuitive equation right here, this penalty we get for moving away from the value of x. So for our interval estimate, we would just go and do all these equations in Excel, and we would get, just do that in black, we would get our 575 minus, for the lower bound, SE y hat star. So we would go ahead and plug this equation in for that part of our margin of error times T alpha over 2. How many standard errors do I have to go out? And then, of course, the upper bound would be plus the same thing. This, of course, is our margin of error, which is a little bit bigger now because we've moved away from the average. So as a review, there's going to be two types of confidence intervals, basically. When we're looking at the mean, the sample average value of x and y, because we know that point is on the graph, we have this simpler version that you're really used to already. But then as we move away from the sample mean, then we have to add this uncertainty related to being farther away from the mean, where we have less information. And that's going to cause a wider interval. So those are the two types of confidence intervals. Remember, confidence intervals are for guessing an average value of y given x. Now, prediction intervals or prediction is when we just want one value of x. So let's go on to some more questions just to show how this is going to work. Notice how this question is going to be a little bit different. What will the home price, so now we're talking about one home price, not an average of a bunch of home prices, for a single 2,000 square foot home be? Answer, the point estimate again is 375. We don't change our point estimate when we go from looking at an average to a single. So remember in class when I said, what if I go grab one random student from across the hall? What's their height? Everybody guesses about the average. Similarly, if I said, hey, I'm going to go take a sample of 30 people across the hall, what is their average height? There's no reason to change your guess from the average in either of those situations. What will happen is the interval. You have more uncertainty with one value because of the possibility of outliers, so the interval is what is going to change. So now our standard error for this case, so I could call it y hat star, but I'm going to call it y hat star star to kind of remember that now we're talking about a single value to differentiate from before when we were looking for an average value. This is going to be a different standard error. And so we're going to have s. That's that SSE over n minus 2, the square root of that, times the square root. So this all looks pretty similar so far. 1 plus 1 over n. So the only new thing here relative to the standard error when we were looking at the average before is this 1. Notice if I put that s inside there, that would be s squared. That is how individual values vary around their mean. This right here, s times that reflects how the sample averages vary around the true average. Well, now since we're looking at one value, we have to account for, well, this right here, s squared, if we put the s in there. That's how individual values vary around their mean. So we have variation in the sample means around the true mean. That's the blue part, the blue circle. And we also have variation of individual values around their mean. And that's where this 1 comes in. Notice we're not dividing by n there because when we're talking about individual values, bigger sample sizes do not help us in that case. So here's our standard error. And now our interval estimate with that is going to be 375, minus T alpha over 2, that's how many standard errors I need to go away, times S 1 plus 1 over n. So our standard error just got a little bit bigger because we're looking at individual values. Plus ... Same thing. So here's the margin of error in this case for individual values of x. Now notice we asked about a special value in this question. What will the home price for a single 2,000 square foot home be? What's special about 2,000? That is at the average value of x, which we know also will occur at the average value of y, 375. We know that point is on the line from what I said above. So now let's ask, well, what happens if I ask about a different value far away from the mean? What will the home price be for a single one home 3,000 square foot home be? So we know that the point estimate from before is 525. We're not changing that just because we're looking at a single value. And now let's just write the interval real quick. 525 minus square root, we have s here, 1 plus 1 over n. So that's the same thing we got before, but now we have to add our penalty for being not at the mean, plus, I'm going to just write it, 3,000 minus 2,000 over sum xi minus x bar squared. So that, the individual variation for my point, this, by the way, is just for this specific $3,000 x value, or 3,000 square foot x value. This is just x star minus x bar. Because we said we're looking for 3,000. We said x bar was 2,000. So I'm just plugging in those values in this case for that number. So notice that now we're looking at an individual value. So we have our 1 there, variation around the mean. We have 1 over n. That's a variation of the sample mean around the true mean. And then we're penalized for going away from x bar. We have less information away from x bar. So then, of course, we'd have comma 525 plus ... for that top end of the prediction interval. So now just real quick, let's think about all this information. So if we had a graph of square feet and home price, we could make a really cool looking graph with all this information, which we'll do in Excel in the follow-up video. So we have our data. We have our regression line going through the data. We know that if we're doing a confidence interval, that confidence interval is going to be the closest at x bar, y bar, right? We know that point is at the graph right there. That x bar, y bar point is on the graph. And we know we will not be penalized for moving away from x bar right there. So that point is going to be the tightest point for our confidence interval. But then as we move away, we're going to get penalized for moving away from the value of x. So we kind of get this bowing out. How much of this bowing out happens will depend on your data. But we can kind of get, that might be our confidence interval. So that's when we're guessing the average value of y given different values of x. Now for our prediction interval, we know we're penalized more because now we're looking at individual values, which vary more, and that's going to be wider than the confidence interval. So then we can get these prediction intervals. That orange will be our prediction interval. And now we could add some pink antennae, fill it in a little bit, and then we have a beautiful looking butterfly. And so we'll try to make a graph like this minus the antennae and the butterfly's body. But this can be a really cool graph, not just to show off your skills in Excel, make a professional looking document. This is definitely something I encourage you to add to your project if you have something that would be amenable to this. This is one of the things that's mentioned in the final project. So I will follow this up with an Excel video to show how to implement everything we just went over in Excel. This should also help a lot with the homework. So again, don't hesitate if you have any questions, and I'll send out an associated Excel video pretty soon.